welcome to the video over chapter 6, Thermochemistry. In this chapter, energy is the main theme. What we do with the energy, how the energy is transferred, what is energy. And so, energy is the main theme. The majority of energy we're going to talk about is kinetic energy. And so we've covered a little bit in this class, and so I'm just going to give you a brief overview with some practice problems to maybe do. And so we said the SI unit for kinetic energy is joules. And the reason why it's joules is that kinetic energy equals 1/2 mass times velocity squared. The units for mass in this case is kilograms times velocity is meters per second, but we square those. And if we look at kilograms times meters divided by seconds squared, this is known as joules. And so one of the things, again, we're going to have to do, like we did with chapter 5, is we're going to have to convert units of a variety of different energies. So you guys might be familiar with kilowatts. We talked about calories in class. So just as extra practice on how to convert units, because the more practice the better we'll become at it. Let's do numbers 33 and number 35 at the end of chapter 6, and this will be due Monday, October 8th. So the coming Monday, and so just again, more practice. The more practice we have, the better, right? And so we talked about energy. What is energy? How energy is formed? That energy can't be created or destroyed based on the first law of thermodynamics or the law of conservation of energy. And so what we care about is the transfer of energy. So thermochemistry deals with energy, but not just energy, but how it's transferred. And so we looked in class, and we will continue to look at class, at the system and the surroundings. And so when energy is transferred from the systems to the surroundings, this is known as an exothermic reaction. The sign for delta E would be negative because you're withdrawing the energy and you're putting it into the surroundings. If energy transfer goes from the surroundings to the system, this is an endothermic reaction with delta E being positive. And so there's two ways this energy can be transferred. The first way is through heat, and that's Q. The second way is work, and that's W. And so there's one way that we can calculate the total energy of a system, and that is delta E is equal to Q plus W, right? So all of the energy in a system is equal to its heat, how much heat it has, Q, plus how much work it can do, W. Now, to practice using this equation, to thinking about the system, to thinking about the surroundings and the and the signs of energy transfer, work transfer, I want you guys to practice number 41 and 43. You'll use the equation delta E equals Q plus W, but you'll have to determine what sign for Q or W you have to use for the problem. And this will also be due Monday, October the 8th. So, one of the things we need to figure out, right? So we want to know the energy, but we also want to measure the energy, right? We want to be able to take a system into the lab and measure how much energy that it has. And the way we can do that is through H. This is known as enthalpy. And so what we see is delta H. So remember, delta means a state function, but the change in enthalpy is equal to the internal energy of a system plus the pressure times the change in volume. Now, this pressure times the change in volume is equal to minus W, right? Because the system is doing the work to the surroundings, so it's releasing the energy, and so that's minus W. When we look at delta E, at constant pressure, so let's say we were to do something in the lab, right? We're going to keep the pressure of the room the same. And so at constant pressure, delta E is equal to Q with a subscript of P telling us that we're at a constant pressure plus W. So what we can do at constant pressure, we can rewrite this equation to look like this. And so what happens is when we can cancel out the work, so the enthalpy is equal to the heat at a constant pressure of the system, whatever we're looking at. This is known as calorimetry. You guys will be doing this in lab and in a coffee cup. Now, Q is equal to the mass of the solution, or the mass of whatever we're looking at, times the specific heat of that solution or whatever else that we're looking at, times the change in temperature. And so the specific heat will be given to you on a problem, or we'll do a problem where we have to calculate the specific heat. But this is the heat equation. So what we can now do is delta H is equal to M times CS of the solution times delta T. Right? And so what we'll see is this is one way that we can calculate delta H. Is we can go into the lab and we can use the calorimeter, check the change in temperature, we figure out the other two variables. So let's do a problem. This will be number 47 at the back of chapter 6. So it says, how much heat is required to warm 1.5 liters of water from 25 degrees Celsius to 100 degrees Celsius? And again, we're going to assume the density of water as 1 gram per mil for the water. So we're given a volume of water. We're given a density of water. We're also given two temperatures. The final temperature, where we want to warm up the water to, and we're also given the initial temperature, where we start this water. And so whenever you're asked how much heat is required or how much energy is required, and you see temperature final minus temperature initial, you know we're going to look for Q. Right? We want to know how much energy it takes to make that change. So if we remember our equation for Q, it's mass, for this case of water, times the specific heat of water, times the change in temperature. But if we remember that this delta means that it's a state function, we don't care the path, we just care final minus initial for everything. Whenever you see that delta, it's always final minus initial. So let's plug in what we know. So we don't know the mass yet. Don't be fooled to plug in this number up here, because that is not a mass. That is a volume. We need mass. Times the specific heat of water would be given to you as 4.18 joules times, or divided by grams times degrees Celsius. So that's a constant. use the units of a constant to help guide what the other things need to be in. So we know temperature final is going to be 100, right? Because we're going to raise it up to 100, and we're going to subtract it from the temperature initial, which was 25. So how do we figure out the mass of water? What unit or what measurement bridges volume to mass? And that's density. And so what we can do is we have 1.50 liters of water. We know that in 1 liter there is 1,000 mils, and we know for every 1 mil there is 1 gram of water. And so what we can now do is we can now plug in that number for our mass of water, and that number would be 1,500 grams. And so now we have everything. So Q is going to equal 1,500 times 4.18 times 75. When we do all this, I told you guys we're going to work in big numbers. It's going to be 47,0250 joules. And so we are allowed 3 significant figures. If you look at the question, we'll forget the density being 2. We're giving 3 significant figures. So our answer could be 4.70 times 10 to the 7th, or 10 to the 5th, excuse me, joules, or 470 kilojoules. Depending on what your answer needs to be in will determine whether you give joules or kilojoules. Usually we just leave it in joules. Now, does this make sense? We're raising the water by 75 degrees Celsius. It's going to take a lot of energy to raise not even a lot of water, right? Because we have 1.5 liters. So this number makes sense. And notice the units. It's in joules because we're talking about energy. So I want you... So to practice this type of problem, I want you to do number 49. And I want you to do that by Wednesday, October the 10th. I also, to practice something very similar to this, and to go to the equation we saw before, I want you to try number 53. But to do 53, you have to keep in mind that delta H is equal to delta E plus P delta V. Alright, so that is the equation that you will need to kind of go through number 53. The other thing you'll need for question number 53, erase this so I can get a little bit more room, is work has to be in joules, right? Because we're talking about energy. And this SI unit for energy is joules. However, if you look at P delta V, pressure will be in atmospheres, volume will be in liters. So what you end up with is atmospheres times liters. And what we need it in is joules. So 1 liter times atmosphere is equal to 101.3 joules. This is a very important conversion factor. And so just keep that in mind as you work through number 53. If you have any questions, then let me know and we can work together in class. That'll also be due on the 10th, on Wednesday. So we're talking about heat, and we can measure energy through calorimetry. We can also calculate how much heat can be transferred, or how much energy can be transferred between different objects. And so we know that Q is mass times specific heat times change in temperature. We also know that Q of the system has to be minus Q of the surroundings. Because when you have energy leaving the system, it is entering into the surrounding. Or if it's leaving the surrounding, right, they're opposites. And so what we can do is we can expand our Q equation to look something like this. To where we have mass of the system times specific heat of the system times the change in temperature of the system is equal to the negative mass of the surrounding times specific heat of the surrounding times change in temperature of the surroundings. It is a lot. It seems like a lot. But let's go ahead and look at an example. We'll look at a number 69 in the back of your book to look at this. And so number 69 states two substances. So we have substance A and substance B. And what we have is there are different temperatures. And what we do is we put them in together. And obviously what will happen is when we put two things at different temperatures together, the heat transfer will occur between the warmest one to the coldest one. And so the mass of substance A is 6.15 grams. Its initial temperature is equal to 20.5 degrees Celsius. The mass of substance B is 25.2 grams, and its initial temperature is 52.7 degrees Celsius. It says the final temperature of both substances at thermal equilibrium. So what does it mean for two substances to be at thermal equilibrium? What that means is that there are two different ways, or at thermal equilibrium, the transfer of heat between A and B will not be occurring anymore. So that will be the final temperature. So the final temperature for both substances is 46.7. Because remember, at thermal equilibrium, no more heat transfer occurs. So the final temperature for everything in those systems is 46.7. We find out that specific heat capacity of B is going to be 1.17. And that's joules, grams, degrees Celsius. We want to find out the specific heat of A. So, let's look at our equation here, and we can start plugging in some numbers. Again, you will be given this equation on an exam, but I will not tell you how to use it. So, you might ask then, well, Dr. Bishop, does it matter which one is the system and which one is the surrounding? It does not matter. You solve the problems the exact same way. So we're going to put A as the system, and we're going to put B as the surrounding. But before we do that, let's go ahead and calculate delta T before we plug anything in. So remember, delta T is equal to T final minus T initial. And if you would like to, you can add that into this equation here. So if you wanted to write this into there to help you see where the temperature is going, that is perfectly valid. I'm just going to go ahead and do it out here on the outside, not add it into the equation just because of the timing and the amount of space that I have. And so what we're going to do is temperature final for A minus temperature initial for A. So delta T for A is going to be 26.2 degrees Celsius. We have final temperature minus initial temperature, and what we get is a minus 6 degrees Celsius. Now, I know what you're thinking. This minus should not happen. keep it there. Because remember, we're talking about calculating heat transfer, and so minuses and positives are very important. And so keep the minus there. So let's plug in what we know into our equation. So we know the mass of A, right? Because remember, we said this was our system, this was our surroundings. And so we know the mass of A is 6.15 grams times the specific heat, we're trying to find that, times the change in temperature. We said was 26.2 degrees Celsius. That's going to equal the negative mass of our surrounding, 25.2 grams, times the specific heat, 1.17, and then joules divided by grams times degrees Celsius, times the change in temperature, which we said was -6. So now, if you want to do it here, you can. If you want to do it later, you can. But we know that since it's a minus, we'll save it for the next step. Getting a little ahead of ourselves. So let's go and erase all this, because now we have our numbers in the equation. Alright. So when we calculate this, we get 161.13 times the specific heat, right? Because that's what we're solving for. And that is going to equal 176.904. Now, the reason why this is now a positive sign is because we had a negative here multiplied by a negative. And so it has to be a positive. Specific heats have to be positives. So if you get a negative sign on your specific heat, then you know there might be a step that's missing or something happened with the math. So, let's solve for specific heat, and it's going to be 1.10 joules divided by grams times degrees Celsius. And so this is our answer. These questions where we talk about heat transfer can get a little tricky. And so I want you guys to do some practice. I want you to try number 67 and 65. And I want you to do that by Wednesday, October the 10th. This way you'll have a lot more practice figuring out heat transfer and the way things can be transferred. This will end this first half of Chapter 6 videos. The second half, we're going to talk about enthalpy again, delta H, but we're going to learn how to do it slightly differently than using heat and a calorimeter.